Hello everyone, today we're going to look at integration by parts. One of the most important things to remember is that this is a last resort only. You only do integration by parts if you cannot use any other method. Integration by parts undoes the product rule, so typically you'll do it when you see a product. Not every product is a by parts, and not every by parts looks like a product, so that's something to keep in mind. The rule is as follows. The integral of u dv equals uv minus the integral of v du. So it looks a little complicated, but we'll do some examples and it will be a lot easier to understand. But the idea here is that we're going to split our integral into two parts, u and dv. Again, remember it's a product rule, so these things are being multiplied. And then we use u to find du, so we integrate it. We use dv to find v, so we integrate it. So by parts uses both integration and differentiation. And then once we found du and v, we plug it into the formula. The goal here is that this integral is a lot easier to integrate. So we'll see what this looks like in an example. So the integral of x sine of x dx. So we do have a product here, and we cannot use any of the other methods that we know. So what we can do is we can let u be x and dv be sine of x dx, or u can be sine of x and dv can be x dx. So the dv always has the dx, right? Otherwise we won't be able to integrate it. So the idea here is to figure out which part of this function goes with the u, what part goes with the dv. So how do we decide which one we want? Well, there are only two possibilities. So you could just try them both and see which one works. Or there's a really nice thing to keep in mind when choosing your u and dv. So we have a list of things that we like to go through to choose our u. And usually it's called LIPET for the letters in red. So the first one is a logarithm. If one of our factors is a logarithm, we want that to be u. If part of it is an inverse trig, we want that to be u. Next comes a polynomial, then an exponential, then a trigonometric function. Now, why we have this order is because remember that u, we're going to then find du. So we need to differentiate u. And the derivative of a logarithm is a lot nicer than the integral. The derivative of an inverse trig function is much nicer than the integral. The derivative of a polynomial is typically nicer than the integral, but it's not terribly different, so that's kind of why it's in the middle. And then an exponential, its derivative and its integral are basically the same. Same thing with a trig function. The derivative of a trig function is a trig function. The integral of a trig function is a trig function. So that's why those two are at the end, because their derivatives and their integrals aren't really that different. Okay, so we go down the list. We don't have a logarithm. We don't have an inverse trig. We do have a polynomial. Remember that x is a polynomial. It's a monomial, but it's a polynomial. So this means we want u to be our polynomial, which is x, and dv to be the rest, to be the trig function. Okay, so that's what we're going to choose. And then the next thing we have to do is differentiate u to find du. So this is just like what we did with u substitution. Du would be dx. And then we integrate our dv. The integral of dv is v. Remember, v is my variable. The integral of sine x dx, we have cosine, but it's the integral, so it's negative cosine. Okay. We don't need the plus c here because we're going to have that later. So when you integrate, you don't need the plus c if you're in the middle of doing integration by parts. So the next thing is we're going to plug it into the formula. So the integral of x sine x dx is u times v, that was the first part, so negative x cosine x, minus v du. So we get a double negative, that's why it's a plus sign. And then cosine x dx. Remember, if you don't if you don't differentiate correctly, you're not going to have a dx here, so you can't integrate that. So remember to you always need a dx when you've differentiated. And then, again, the idea here is this new integral easier? Yes, right? We know how to integrate cosine x, it's sine x. So we get negative x cosine x plus sine x, and now we have the plus c. Don't forget, you can always double check this using differentiation. Just remember that by parts undoes the product rule, so to differentiate you will need that product rule, and that product rule is going to come up in this case here. But you can always double check it. If I differentiate this guy, I will get x sine x. Let's try another one. The integral of the square root of x times ln of x. So again, we need a u, we need a dv. So again, we're going to go down that LIPET list. And right off the bat, we've got a logarithm. So u is going to be ln of x. dv is everything else. So the square root of x dx. Okay. And then again, we differentiate u. The derivative ln of x, remember, is 1 over x dx. And then the dv will integrate. Again, the integral of dv is v. The integral of the square root of x dx, remember, this is x to the 1/2. So I'll add 1 and then divide by my new exponent. Okay, I'm not going to spend a lot of time doing out these steps, the du, the v, because again, this is stuff that we should know already. So here it is. Du again is 1 over x dx. V, like I just said, is 2/3 x to the 3/2. Again, don't put the plus c yet. We'll do that at the end. Okay, so our integral is uv, that's my first one, minus the integral of v du. Notice I have 1 over x times x to the 3/2. So remember that is x to the negative 1 times x to the 3/2. I add those exponents together, and that's how I get x to the 1/2. So you always have to make sure you're simplifying your v du. So we just have the coefficient of 2/3 and then x to the 1/2. And again, this new integral, much easier to integrate, right? That's just the power rule. You did that in Calc 1. So we get our 2/3 x to the 3/2 ln of x minus 4/9 x to the 3/2. Okay, so don't forget you're going to have this 2/3 plus another 2/3 when you integrate. Notice that this integral here, if I ignore the 2/3, is the same thing that I had just done. That happens a lot when you see a polynomial times a natural log. You end up integrating the same thing twice. Okay, so again, we have the same thing except an extra 2/3 there. And again, you can always double check it by differentiating. Let's try another one. The integral of ln of x dx. Now notice we have not actually done this integral yet. We've done integrals that we get out the natural log, but we haven't integrated the natural log yet. And that's because we need to do it by parts. Even though it doesn't look like a product, we can think of it as ln of x times dx. So we go down our list. Again, the first one right off the bat is L for log. So u is the natural log of x. dv is just dx, or if you want, a 1 dx. Then again, we differentiate u. Again, we get 1 over x dx. We integrate dv, and we get that v is x. If dv is dx, then v must be x. And then we'll plug it into our formula. Again, u times v minus v du, the x's cancel, and we get just the dx in the integral. And remember, the integral of dx is x. Again, it's the same exact one that we just had. So we get x ln of x minus x plus c. And again, you can check it by differentiating. This is a really nice example. You might see it come up a couple other times, hint, hint. So you really want to remember that if you just have a natural log, even though it doesn't look like a product, it is by parts, because we don't know how to do it any other way. And remember, by parts is a last resort. Here's another good one, the integral of e to the x cosine x dx. So we have an exponential and a trig function. If we go down our list, then we get to exponential first, right? The very last ones are exponential and then trig. So I'm going to let u be my exponential, let dv be the trig, and again dx goes with dv. I'm going to differentiate u, and I'm going to get the exact same thing. I'm going to get e to the x, but I'll also have a dx. And then I'll integrate cosine of x, and I'll get sine x. So in this step should be fairly nice, should be easy. Now I'm going to plug it into the equation. uv minus v du is this guy over here. Notice that my integral of v du is not any easier to integrate. I don't know how to do e to the x sine x, but it is very similar to my original guy. I had e to the x, e to the x. I had cosine x, now I have sine x. So the fact that they're similar means that I'm on the right track, and it means that I'm going to have to do by parts twice. So I start with this guy, and we'll plug it back in after. So e to the x sine x dx, I'm now going to do by parts on that equation, or that integral. Again, just like before, we're going to let u be the exponential, let dv be the trig. Differentiate it. Again, I get e to the x dx. The integral of sine is negative cosine. And then I'm going to plug that back into the equation. So the integral of e to the x sine x is negative e to the x cosine x, so that was uv, minus v du. I have a double negative, so it becomes a plus the integral of e to the x cosine x dx. Now the fact that I have the exact same thing as what I started off with really means I did it correctly. Okay, so my last step is to combine these. I'm going to plug in this guy up here. Okay, so the integral of e to the x cosine x dx equals e to the x sine x minus, remember this was the integral of e to the x sine x dx. Okay, but I've just plugged it in from our second by parts. Next, I'm going to distribute the negative. Okay, that's all I did was distribute the negative. And now, remember what we're solving for. We're looking for this guy. I've got one over here. I've got another over here. Whenever what you want is on both sides of the equal sign, you got to put them together. So I'm going to bring this over by adding it to both sides. And so I brought it over, so now I have two of them. I also factored out my e to the x on the right-hand side just to clean it up a little bit. And then I've got an integral equals, and I've got the plus c here too. And then my last step is to just get rid of my 2. So the integral of e to the x cosine x dx equals 1/2 e to the x times sine of x plus cosine x plus any constant. Okay, you're going to have one of these that's very similar in the homework. So remember, you will have to do by parts on this twice. I will not make you do a double by parts on the test though. Okay, so anything on the test that you need to do by parts with, you'll only have to do it once. So that's something to keep in mind. Okay, so let's try another one. We've got the integral of a tan inverse of x dx. Again, it doesn't look like a product. There's only one thing there, tan inverse. But we don't know how to do this any other way. Right? We can't do u substitution. We can't do any of our trig things that we know about. So by parts is the only thing that we can do. Also, remember that on our list, inverse trig comes second. So inverse trig, tan inverse, will be u, which means dv has to be dx. So we will differentiate u. Remember, the derivative of tan inverse is 1 over 1 plus x squared. And then we need to multiply by dx. Okay? And again, the integral of dv is v. The integral of dx is x. So du is dx over 1 plus x squared. V is x. We'll plug it into the formula. I got uv, x tan inverse of x, minus v du. So x over 1 plus x squared dx. This guy is a really, really nice u substitution problem. Right, I want u to be 1 plus x squared. So du is 2x dx. So I'd have to divide by 2 and I'll get my x dx here. So this is just a u substitution. Right? Always look for u substitutions first. They're the easiest type of integration. So I get my x tan inverse of x, and then my u substitution, well, that will become a natural log. So again, I have negative 1/2 from the 2x, and then it's just 1 over u, so that's ln. And then I've got the absolute value of 1 plus x squared. So don't forget that in general, whenever you're integrating 1 over u, it's ln of the absolute value. In this case, you don't actually need the absolute value because 1 plus x squared will never be negative. But it's not bad to just keep it there just to remind you that in general you do need that absolute value. And then plus c. Okay? And again, you can always check it by differentiating. Okay, let's try another one. The integral of sine x times ln of secant of x dx. The first thing you want to notice is that you have a composition here, ln of secant of x. So don't forget, u substitution undoes the chain rule. The chain rule is for composition, so you always want to check, is this a u substitution problem? So u would be secant x. And if that's true, what would du be? Well, the derivative of secant x is secant x tan x. And is that what I have over here? Clearly no. So because sine of x is not a multiple of secant x tan x, I cannot do u substitution. But you always want to check that whenever you have a composition of functions. Right, so I can't do it. Doesn't help me. So I am going to try by parts. And again, the first thing I want to look at for u's is a log, which is what I have. So u is going to be my log. And dv will be what's left. So u is ln of secant of x. dv is sine of x. Remember, this is a product rule. So it's not that u is ln and dv is secant. Secant's part of ln. That's one factor. So u is ln of secant of x. dv is sine of x dx. Then comes the differentiation and the integration. Integration of dv is fairly easy, right? V is going to be, again, I know it's cosine because it's sine, and then it's the opposite of differentiation, so it's negative cosine. Remember that the derivative of ln of something is its derivative divided by itself. The derivative of secant is, as we just said, secant tangent, so it's going to be secant tangent over secant. This simplifies rather nicely, the secants cancel, and I've just got tangent of x. So the derivative of the natural log of secant of x is tangent of x. And again, as I mentioned earlier, v is negative cosine of x. Okay, so we're going to plug those into the formula for by parts. We get this guy, negative cosine x ln of secant x, plus the integral of cosine x tan x. And we have that double negative from the formula and then that negative, so I have a plus sign here. Cosine x tan x right off the bat doesn't look very pretty, but remember that tangent is sine over cosine. So my cosines cancel, and I'm left with just sine. Integral of sine is really nice. So we get negative cosine x ln of secant x minus cosine x plus c. And again, you can always double check it by just doing the differentiation, and then you might have to do a little bit of trig simplification in there also. Okay, here's our last one, the integral of x e to the x squared dx. I have a product here. I've got an x, I've got an e to the x squared. So you might want to think that I'd let u be my polynomial and let dv be my exponential. But don't forget, by parts is a last resort. This is not a by parts problem. Okay, again, we have a composition here, so I need to look at that first. Every time you see a composition, you have to think, is it a u substitution? So I'm going to let u be my inside function, which is the x squared. Du will be 2x dx. And this is what I have here. So this is a u substitution, not a by parts problem. The biggest mistake I see people do on the test is they do by parts when they should have done a u substitution. And then they get really complicated. They try doing by parts a second time, even though I tell them you're not going to have to do it a second time. And then they try doing it a third time, and then they just give up. So remember, just because you see a product does not mean it's a by parts problem. Every time you see a composition, you have to ask yourself, is this a u substitution problem? Which again, this one is. So I just divide by 2, and I get this, which makes my u substitution really nice. I just went through that already. So my u substitution, I get 1/2 the integral of e to the u du, which is just 1/2 e to the u plus c, which is 1/2 e to the x squared plus c. Okay, so again, it's really, really important that you don't just blindly start doing by parts. Always look for something else first. By parts is the last thing you look for. Okay, so try out the homework. Let me know if you have any questions, and good luck.